Okay, so last time we have seen what are monoidal categories and how to enrich over a monoidal category. The home sets, I mean in simple terms, home sets carry some extra structure. So apart from being locally small, so in particular we are going to be interested over Ab-enriched categories. So then there is a name for that. So those are known as pre-additive categories. These are precisely categories which are enriched over the category of Abelian groups. What does that mean? Yeah, in simple language, it means that every home set is an Abelian group, and moreover composition is bilinear. Composition of morphisms is bilinear, right? That's all it means, Ab-enriched category. Its a set is important. It's a locally small category such that everything has appropriate, every home set has a structure of an Abelian group. Now, let us look at some example. You give me one example of an Ab-enriched category. Category of Abelian groups, very good. Okay, then more generally, category of R modules, where R is any ring. Okay, anything else? You only know these two examples, nothing more? Two classes of examples, I should be precise. Okay, what about a single object pre-additive category? Okay, let's take a pause and think about it properly. So we are given, so single object means we are given a category, let's say C, and then C star star, the endomorphisms in this C star star, this is an Abelian group. Okay, which means it has got some. So in general, what happens, like what is a single object category, tell me? It is a monoid with respect to composition. Very good. Composition, it is a monoid. So now what kind of structure do we have? We have C star star is a set because it's pre-additive. Then it has got some addition structure, plus and 0. Then it has got a multiplication structure, namely composition. And then it also has got the identity structure. What is this? Such that composition is bilinear, which means composition distributes over addition on both sides. So what is this a definition of? A ring. It's a unital ring. Okay, so basically this is same as a ring with unity. So whatever role a monoid played in the set world, in the locally small setting, the same role in the pre-additive world a ring is playing. Okay, so very good. So now we know what is a ring. A ring is nothing but a single object pre-additive category. Understood? Okay. So let us do something more. I mean, there are other names also, but let me just say that. Yeah. So set star is a monoidal category. Set star is a monoidal category with respect to smash product. Smash product as in anything. So how do you take product? Set star is A comma A naught, B comma B naught. These are two objects. So you take A cross B, and then you are going to take anything which corresponds to which has A naught or B naught. You are going to identify that into a single point. Yeah, so it's an equivalence relation which identifies all such pairs. So A0 comma B as well as A comma B0. So that's a set star. So that's a monoidal category, and set star enriched category is known as a pointed category. Okay. So maybe I will just, maybe I should write it somewhere above. So it's set star enriched category. This is the notation for smash product. Yeah, and it's the, you have to write a pair. Yeah, singleton star, comma star. Yeah, so enriched is pointed. I mean, I'm just giving you this name because you might need it at some point, and there is also some other name like CMON, commutative monoids. So commutative monoid enriched category, they are known as semi-additive. Some of the results that I am going to present today, they also hold in slightly weaker settings, and I will tell you about them, yeah, whenever appropriate, but these are just some names. Yeah, pointed category. For example, groups is pointed. Groups is not pre-additive, yeah, because groups could be non-commutative, non-abelian. So therefore, groups is just pointed. It's not even commutative, so it can't be CMON enriched. Okay. Now, once we have this, last time we did not define it, but let's define a functure appropriately. So suppose C and D are pre-additive. Yeah, then a functure f from C to D, I mean, I should say an enriched functure, an Ab-enriched functure is called an additive functure. Okay, so this is a definition of an additive functor. It should behave well with respect to the enrichment. What is the enrichment? Abelian groups. So what does this mean really? That this is an additive functor. So for any, yeah, i.e. group homomorphism between, correct, okay, for any A and B objects of C, yeah, the map from CAB to DFAFB induced by F is an Ab-morphism, which means it is a group homomorphism between two abelian groups. So this is the notion of enriched functure. So basically, yeah, I mean, whatever should happen does happen. That's the slogan here. Yeah, so Ab-enriched functors are called additive functors. We don't call them pre-additive. Yeah, we just call them additive functors. Any questions so far? Okay, I'll give you one more example in this list, yeah, over here, and that is a ringoid or a ring with many objects. This is defined to be a small pre-additive category. Some people will also say skeletally small, but I'm just taking the definition to be small. So small pre-additive category, you understand, it's basically just a diagram in the category of rings with unity. So when like whatever results that are true for rings usually are true for rings with many objects as well. Our normal notation for this is going to be R for this, and for a ringoid it's a curly notation, capital notation for a ring and for a ringoid R. So usually you can replace capital R with a curly R without any problem. Okay, now that we have defined an additive functor, yeah, let's try to understand the additive functors. All of you know functor categories, yes? What are the objects of the functor category? Functors between two fixed categories. And then what are the morphisms? Natural transformations. Okay. Now, whenever we are talking about an enriched situation, then we assume that our categories are enriched and our functors are also enriched. So we are going to use the notation CD to denote the Ab-enriched functor category. I mean, I'm not going to specify that it is Ab-enriched situation, you just have to understand. Yes, so the same notation as functor category, but we are just going to ask for something more on the objects. Okay, so what will happen if you are starting with a ring and then I take this? The category of all additive functors from a single object pre-additive category to the category of Abelian groups. So how many objects are there in R? 1. And that object has to map to some Abelian group, and then for every endomorphism of that unique object, like every element of the ring, there is some map which is an endomorphism of that M. So it becomes a module. Okay, so this is the category of left R modules. Okay, what if you want to do R-op? R-op ab is the category of all right R modules. I mean, do you understand that R-op also has got an Abelian group structure? It only reverses the multiplication. The home set doesn't really change, so everything just happens naturally. So the definition of enrichment is symmetric. Yeah, it's a bilinear map. Composition is bilinear. So therefore, it doesn't matter whether you distinguish between left and right. Okay, so in general, like R-op and R, if you make that distinction the opposite category, then you will get left-right distinction. That's all. Okay, so modules are like representations. We have seen that. Yeah, G sets, M sets for a monoid M. Yeah, so or G vect K. Yeah, all K linear or F linear representations of a group. So modules are just representations, and module homomorphisms are actually natural transformations in an appropriate setting. Category R is the single object pre-additive category. I have written it here. Single object pre-additive category is a ring with unity. Okay, and you can obviously, I mean, similarly talk about the ringoid. Okay. So left and right modules, now you already know, I mean, these categories, these are just functor categories. So let's start proving some results, some simple results. Suppose A is pre-additive. Now I will change the notation. You can also take pointed here because you will see you don't need lot of structure. Suppose A is pre-additive, then for an object I of A, TFAE, the following are equivalent. The first property is that I is initial, then I is terminal, and third property is that the identity on I is the zero morphism in the home set. You understand zero morphism? Yeah, zero morphism means it is the zero of the Abelian group, the Abelian group structure that we have. Okay, so then for any object we have this. How do we write a proof? I will only prove 1 and 3 are equivalent. Yeah, I won't prove 2 because 2 is dual of 1. Okay, so 1 implies 3. If I is initial, then can you immediately conclude that the identity on I, the home, I mean if it is initial, then home II has to be singleton. Well, that singleton has to be identity and it also has to be 0 because it's an Abelian group. So done? Okay, I am not writing that. And what about 3 implies 1? Well, here you need a little bit of proof that suppose identity is 0, then what do we know? For any morphism F from, so for F from I to A, yeah, what do we know? We know that F composed with the identity has to be equal to F. But what is F composed with identity? Well, F composed with 0 has to be 0, which means this is, and where is this 0 living? It's living in AIA because AIA is also an Abelian group. So what did we prove? That every morphism is the 0 morphism. So obviously there is a unique morphism and we are done. Yeah, hopefully no question here. Okay, so because these are equivalent, what did we show? That a pre-additive category or a pointed category has an initial object if and only if it has a terminal object. So any object, so initial plus terminal is called, is the 0 object. This is the definition, yeah. A category has 0 object if it is both initial and terminal. So, so in denoted by 0. Yeah, this is an object. So 0 will be a notation for an object. We will not use I or T or 1. We will use 0. And it is also a morphism in every home set. And okay, in fact, if 0 object exists, then for any A and B in A, yeah, the 0 of this home set AAB is actually the unique morphism composed, it is the composition of these two unique morphisms. A to 0 you will always have a unique map, 0 is terminal, and 0 to B you will always have a unique map, 0 is initial. So this composition is actually the 0 in that home set. Any questions? Okay, so let's prove another fact. So I'm just going to keep taking the same assumption. Suppose A is pre-additive, although I mean you don't need this strong assumption. So for objects A, B, C of A, the following are equivalent. Can you see the theme from this first result that we proved? The theme is that initial and terminal is same. Now I'm going to show that finite products and finite coproducts are same. So everything is self-dual. Duality principle is the key. Okay. For abelian categories or pre-additive categories, duality principle is very much useful. So what things are useful? So there is a cone making C a product of A and B. Okay, second condition, there is a cone under the diagram now. So AB, this is nu 1, this is C, making C a coproduct of A and B. And finally, there are morphisms. Okay, now consider these morphisms. So A, C, B. I will write both of them. Yeah, this is nu 1, this is pi 1. Then this is nu 2, this is pi 2. Such that, yeah, now nu I pi j, sorry, pi I nu j, first include then project, is equal to delta ij. Delta ij is the Kronecker delta. And nu 1 pi 1 plus nu 2 pi 2 is equal to identity on C. So, okay, you should ask some natural questions once you process the information. So, what we are saying in this third condition, that you start at A and then return to A, pi 1 nu 1 is identity on A. Then start from A, go across go using nu 1 and then pi 2, then you will reach 0. And when you start from C and do both circles, now you have got two different maps. Now those two maps, you have to simply take the sum of them. You can do that because home CC is an abelian group. So you take the sum, you will get back identity. Right? So this is what we are trying to say here. And these three conditions are equivalent. Okay, so on a higher level, what we are trying to say, that binary products are same as binary coproducts. And we'll call them byproducts. And we'll use the notation direct sum to denote this. Usually for product, what do we write? Cross. And for coproduct, we write plus or disjoint union. But here we are going to say direct sum. Yes, finite products and finite coproducts coincide. No, it's not true for infinite products or coproducts. No.
So, but does there exist a specialized version of such flavors where these infinite coproducts, useful version of
some version of an abelian of an pre-additive category in which infinite products and infinite coproducts coincide? No. They will always be different. So normally infinite products are the direct products. So you basically take tuples of all elements, and the direct sums, infinite direct sums, are those where the tuples are infinite but only finitely many entries are non-zero. That's how we usually work with things. So infinite products and infinite coproducts, they will differ. They are not isomorphic, but finite ones, they do coincide. Okay. Let's try to prove 1 implies C. So we are given that this is a product diagram. Okay, so you have to take A, B, C, pi 1, pi 2. Now I am suggesting start with A and form a cone over the base diagram. From A you can take identity, from A to B you can take 0. That's the only thing that you know for sure exists. Then because this is a product, there must exist a unique map. This unique map is your new one. Okay, let me write it here. There exists a unique map, call it new one, which makes pi 1 new one equal to identity and pi 2 new one equal to 0. Do the same thing with B, identity on B, 0 map to A, you will get new 2. Okay, what remains now? We are supposed to show the last identity. There are 5 equations to satisfy. We have shown 4. We have to satisfy the 5th one. Okay. So for the 4th one, consider this. So we are going to use uniqueness of factorization. Okay. So pi 1 composed with new 1 pi 1 plus new 2 pi 2. Consider this. What will it give us? Pi 1 new 1 is? Pi 1 new 1 is 1. So this will be pi 1 and then plus pi 1 new 2 is 0. So I am not adding anything. So which is equal to pi 1 composed with 1 sub c. Okay. And similar thing holds for this. So this is pi 2, which is same as pi 2 1c. So now you can see that there is a cone from C to A and B, and there are 2 different factorizations of the given cone through itself. Is it possible? It's always unique. So by uniqueness, you can conclude that new 1 pi 1 plus new 2 pi 2 is equal to is identity. Yeah. So use universal property. Okay. So it's the factorization of the limit cone through itself. So therefore we get this. Okay. What about 3 implies 1? So now we are given these morphisms. We have to show that there exists a unique factorization. Like it's a product diagram. Okay, so suppose we are given this AB. This is definitely a cone, yeah, nothing doubtful about that. But then we are given some D and some morphism, let's say F and G from here. I need to find a factorization in between. Can anybody suggest me what that factorization would be? No, we are trying to prove that there exists a factorization and it is unique. Yes, so define a map H from D to C by, I mean the only thing that you can do, nu 1 F, yes, nu 1 F plus nu 2 G. Okay, then verify that this works. and then conversely, I mean, sorry, not conversely, you in addition and verify that this is the only solution. This is the only factorization. Means you have to verify that this is a factorization and it is the only factorization. So therefore, thanks to this result, now we can define byproducts. So byproduct is binary product plus binary coproduct, and we denote it by the notation A direct sum B. Okay, so direct sums of vector spaces, they are both products as well as coproducts, binary versions. Yeah? Infinite byproducts do not exist. Infinite products and infinite coproducts, if they exist, then they do not coincide. Is that your question? Okay, I will have to think about that. By the way, there was a question last time. Yeah, I should say something about that. There is a paper by Ellenberg and Kelly about monoidal categories. Yeah, so please try to look at that. Somebody asked me last time about enriched, self-enriched. Yeah, closed monoidal structure is self-enriched. What about the converse? I did not verify the entire thing, but I believe that if you take the category of small categories, cat, then it is enriched over cat itself via another way. Yeah, and that it's not the usual collection of all functors kind of thing. But I am saying you only remember the set of functors from C to D. Take that as your internal home definition, treat that set as a discrete category. Then I want to claim that this particular internal home doesn't have a left adjoint, which is the product, which is a this monoidal product. Try to verify that. Yes, I haven't checked that whether by infinite byproducts, I mean infinite products and infinite coproducts are not the same, but maybe after doing one more theorem next week, we will be able to prove that. Okay, now there is a definition. Say that a pre-additive category A is additive if it has a zero object and byproducts. Okay, so this is definition. Like we are trying to add more and more limits and co-limits. So an additive category has finite products and finite coproducts. Yeah. Okay, what would be the next thing? If we know we are trying to add more limits and co-limits, then what else is remaining? Equalizers. Very good. So equalizers have got a special name here. They are called kernels. Okay. So kernel, this is a definition. So suppose F is a morphism. I mean, I don't really need it to be an additive category in a pre-additive category. With equalizers, define the kernel of F to be the equalizer of f and 0. So, okay, just a bit of notation part here, like I am taking A to B. Yeah, so the kernel is actually this whole thing. So kernel is k comma k. Yeah, by continuing our tradition. So k comma k is the kernel. So the morphisms are important. Yeah, unlike in algebra where we only consider this capital K as the kernel object. Here it is important to consider the morphism as well. We will usually refer to the kernel as the inclusion of that K into A. Kernels are regular. Yeah, we are simply saying that it is equalizer of f and 0, right? 0 is a morphism possible here. So therefore, kernels are regular monomorphisms. But in this world, in additive world, we usually call them normal instead of regular. Okay. So this is the kernel. So say that a mono M from A prime to A is normal. Oh, so in an additive category, additive or pre-additive, is normal if it is the kernel of some morphism. Okay. Now, how to test whether it is kernel of something? Yeah, that something is like it's a variable ranging over all morphisms in the category. But we don't really have to go that far. Yeah, in algebra, when you study kernels, then simultaneously also study the dual notion of co-kernels. So, if it is the kernel of its own co-kernel, that is the idea. Okay, so kernel, and similarly you can define co-kernels. Yeah, so okay, maybe I should say one more property. So equalizer of a parallel pair f and g is the kernel of f minus g. Because you can add, so you can subtract. So f and g are parallel, you simply change them to f minus g comma 0. Subtract g from both of them and then you get the kernel. Okay, so normal, mono and normal AP, you can also define the dual notion. Yeah, normal is just regular. Okay. So another simple thing that you can prove is that if kernel of f is 0, then f is monic. Can you prove that? How do you show something is monic? Okay, so let me start with this A and B. This is f. Its kernel is the 0 morphism. Well, 0 I can always take it to be 0. This is the 0. Then I have to start with a pair of morphisms on which side? C to A. Very good. Let me call them G and H. What will happen? G and H both won't factor through 0. See, what do we know? Suppose Fg is equal to Fh. Then F into G minus H is equal to 0. Okay, so anything which factors, like anything which composes with F to give 0 has to factor through. Therefore, there exists a K from 0 to C such that tell me. Yes. Sorry, C to 0. Such that H minus G minus H is equal to 0 composed with K, which is 0, which means G is equal to H. Okay, so kernels are obviously monic. You can define co-kernels dually and prove the same properties. Okay, now comes another interesting result. So this is something I already said, that suppose A is pre-additive, with kernels and co-kernels. Okay, then F is a morphism from A to B, is a normal mono if and only if F is isomorphic to the kernel of its co-kernel. Okay. Now here I am using isomorphism for two morphisms. F is a morphism. Yeah, F is given to be a mono. F is a morphism, it's a mono with target B, and kernel of co-kernel of F is also another mono. So when I am talking about this isomorphism, what do I really mean? There is a morphism, there is an isomorphism from A to the domain of the kernel of co-kernel. Yeah, or I mean in simple words, it is simply isomorphic as subobjects. You know subobjects, yeah, subobject posets, preorders, we have seen that. So whenever it is normal mono, then we have F is isomorphic to kernel of its own co-kernel. We don't have to go finding it. Okay. One side is obvious. Which side? Backwards. Because we already know F is isomorphic to this thing. So only the forward direction is supposed to be done. Okay, I'm going to draw a diagram now. This is some diagram chasing kind of argument. So please pay attention. If you simply write the final diagram, then you will not understand what I'm doing. Okay, so what do we start with? We are given F. Then F is the kernel of something. Yeah, this is the forward direction. It is a normal mono. So F has to be a kernel of some morphism from B to C. Let me call it G. Yeah, so suppose F is the kernel of G. Okay. But at the same time, I can also talk about its own co-kernel. And this is the morphism Q, which we can also write as co-kernel of F. Correct? Every morphism, like it has kernels and co-kernels, so I can define its own co-kernel. Right. Now the same thing we can do, like Q is a morphism, I can define its kernel. Okay, let me call that E. and from E I have another monomorphism which is K, which is kernel of Q. So kernel of co-kernel. Now observe that QF, I mean GF is equal to 0. Okay, what does that mean?
C and D are isomer. Q and G are isomer.
No. No, no, no. GF is equal to 0. It means that G factors through Q. It has to factor through the co-kernel of F, which means there is a morphism over here. Okay, I mean we obtained it as a, maybe I should write it, there exists unique. Yeah, this is called H, let's say. Okay, now similarly we should talk about this. So QK is equal to 0. Yes, because K is the kernel of Q. So QK is equal to 0. Therefore, HQK, which is actually, tell me, right. So GK equal to HQK is also equal to 0. What does that mean? So therefore K factors through F. Which means there is a morphism from E to A. Very good. Let me call that L. Okay, now one last thing. Yeah, so we need a morphism in the opposite direction. So GF is equal to 0. Yes. Okay, so GF is equal to 0. That means what is G? It is HQF. So HQF is equal to 0. What does that mean? There is a map from A to E. Directly, can you conclude that? See, what do you need? You need to show that QF is equal to 0. How will you conclude that? Very good. You don't need this. QF is equal to 0 since Q is the co-kernel of F, and therefore F must factor very good kernel of Q through kernel of Q, which is equal to K. So therefore there exists a map here, let's call it M, and now what did you get? L and M are two morphisms, you can take their compositions, but F and K are both monos. So since F and K are monos, M and L are inverses of each other. And we are done. Like you do FLM and just F. Yeah, you will have to show that they are same. FLM is equal to F. You show that, then you are done. Okay. So this gives us some new piece of information, some new piece of notation. Yeah, notation. So for a morphism f from A to B, image of f is defined to be the kernel of its co-kernel, and co-image of f is defined to be the co-kernel of its kernel. So image is not an object. Just like I said that kernel is not an object, it's a morphism. Image is also a morphism. So in set theory also, yeah, we have image factorization of any function. A to B function is given, the image is actually the inclusion of the set theoretic image into the codomain. That is the image map, and the co-image map is the other one, the surjection onto the set theoretic image, that is the co-image. And we have something similar over here. Any questions so far? So now we will prove this image factorization exists in any okay, maybe I should define an abelian category first, then we will talk about this. Okay, a pre-additive category A is abelian if, first of all, it is additive. Second condition, A has kernels and co-kernels. And third condition, each mono in A is normal. And similarly, each epi is also normal. Okay, so first two conditions, what they imply together? Yes, Cartesian and co-Cartesian. Which is bicartesian, yeah, language is bicartesian. And then the last one says that it's regular as well. And if you come across regular categories, then regular pre-additive categories are precisely abelian categories. Okay. Some important properties about abelian categories, yeah, or maybe we'll do it slightly later. Let's first prove the result about image factorization. Okay, so suppose A is abelian, so that we can assume everything. Then for any f from A to B, there is a factorization. So A to B to I. This is image f and this is co-image f. Into a regular mono, a normal mono, or as a normal mono followed by an epi, or dually also. Yeah, I mean both of those things happen. That is unique up to isomorphism. Such a factorization is unique up to isomorphism. Okay, so I mean, one thing I should do perhaps before this particular thing is that if you are given any particular morphism, yeah, let me write it over here. If you are given any morphism like this, and then you have its co-kernel of f, and then you take its kernel, yeah, which is the image of f. Then the co-kernel of f is, I mean, isomorphic to the co-kernel of its image as well. Yeah, image is not going to give you anything different. Maybe up to isomorphism it will like, yeah, it will be equal up to isomorphism. Yeah.
As a normal epi followed by a
Oh, normal AP followed by a mono. Yes, thank you. I mean, both versions, yeah. Actually, they are both, yeah. Both of them are normal. We are working in an Abelian category.
yeah, but the epi comes first.
Yes, that's correct. I mean, normality is not really required, but you can also prove one half of this result in a semi-additive category. That it's normal AP followed by a mono, or mono and beforehand you have a, I think it's called a pseudo AP. Pseudo AP is a morphism whose kernel is, co-kernel is 0. So you can do it both ways. Normal AP followed by a mono. This was just English problem. Thank you. Okay, so let us prove this. First of all, let's show uniqueness. These are relatively simple proofs, and I also want you to get a flavor of how these diagrams or arrows are chased. So that's why I'm doing these proofs. Okay. So for short, I'm going to call this co-image as Q and image as I. Okay, Q is a good notation for a quotient, yeah, and I is for inclusion. Okay, so this is about image factorization. So for any map G from B to C, where it doesn't matter where we are, like B to C, it doesn't matter. So GF is equal to GIQ is equal to 0 if and only if GI is equal to 0. So we are assuming that we have such a factorization where Q is an epimorphism, so you can cancel it, yeah, from both sides. So GIQ is equal to 0 if and only if GI is equal to 0, which means GF is equal to 0 if and only if GI is equal to 0. I gave you a proof of that, the statement that I wrote above, right? So therefore, co-kernel of F is isomorphic to co-kernel of I. Okay, so therefore, as subobjects, of B, I is isomorphic to, oh sorry, I think I'm making a mistake here. I should not have written this. I should say that suppose there is a factorization, yeah, and then I'm doing it for this. This is an epimorphism and then this is a monomorphism. This is I and Q. So suppose this is given. This commutes, okay, where this is mono and this is AP. Then for any map, GF is equal to 0 if and only if GI is equal to 0, and therefore co-kernel of F is isomorphic to co-kernel of I. Yeah, because they are going to become 0 exactly at the same time. So as subobjects of B, I is isomorphic to kernel of co-kernel of I, which is isomorphic to kernel of co-kernel of F. Okay, so because co-kernel of F and co-kernel of I are isomorphic, I get the second isomorphism. How do I get the first one? I is isomorphic to kernel of co-kernel of I, because we just showed that above. Yeah, that for a monomorphism, F is isomorphic to its kernel of co-kernel. Yeah, so this is about the result above. Okay, so as subobjects, I is isomorphic to this, and Q is the unique factorization. Of F through image of F. So done. Yeah, this is the unique factorization. So we have shown uniqueness. We have a standard thing and then we have shown uniqueness. Now what remains, like what is more important in this particular result is the existence. And for existence, once again I will need your undivided attention. I am going to draw a diagram and you should try to follow this with me. Okay. So let us start with A to B. This is our F. So we want to show that such a factorization does exist. And we are going to use the image. Image is confirmed. What do we need to do? So like how do we confirm the image? Like obviously I have got co-kernel of F to C, and then I have its kernel. So this is, let's say, I equal to image of F. Then because co-kernel F composed with F is equal to 0, I must have a factorization of F through I. Yeah, F must factor through I, because this is co-kernel F composed with F is equal to 0. Still with me? Okay. Now, after that, this is Q. So from Q, I can construct its own co-kernel. So this is my co-kernel of Q. What do we need to show? That this particular co-kernel is 0. We want to show that. Okay. But at the same time, I can also say I can take the kernel of this. So J, this is a mono, obviously. So this is image of Q. Okay. Now, this much diagram we have.
So then we have another composition which is 0.
Yes, so co-kernel of Q composed with Q is equal to 0. So it must factor through its kernel, like the kernel of co-kernel. So there exists an R. Okay. Now let me say something. So for any morphism G from B to E, yeah, Gij is equal to 0. Okay, so G is here. B to E. So Gij is equal to 0. What does it imply? This triangle commutes, so therefore Gij_r is equal to 0. Yeah, if Gij is equal to 0, Gij_r is equal to 0, which means Giq is equal to 0, which means Gf is equal to 0. Okay. And if Gf is equal to 0, then there must be there must exist then G is equal to H composed with co-kernel F, and then what will happen? H composed with co-kernel F.
Co-kernel F is the co-kernel of IIT.
Co-kernel of, no, co-kernel F is not co-kernel of Ij, but co-kernel F is same as co-kernel of I. Yeah, because that's the image. So, can you show that Gi is equal to 0? Therefore, Gi is equal to H co-kernel Fi, and I is the co-kernel of F. So therefore, this is equal to 0. Okay, what did I show so far? Gij equal to 0 implies Gf equal to 0, and Gf equal to 0 implies Gi equal to 0. Therefore, yes, so Gij is equal to 0 if and only if Gi is equal to 0. This is what we showed. Okay, understood this part? So therefore, what will happen? The co-kernel of I is, equal to or isomorphic to co-kernel of Ij. Let me write isomorphic, and therefore I is isomorphic to Ij as subobjects of B. We used every single piece of data in this diagram, yeah, so far. So I is isomorphic to, so therefore what can we conclude? J is an iso. Huh? How do I define morphisms between two morphisms? We are working in the subobject pre-order. Yeah, slice category, simple idea. Yeah, slice category or subobject, in particular just a monomorphisms with the same target. Okay, so I is isomorphic to Ij as subobjects of B, and therefore J is an isomorphism. That much you understood? When is the image an isomorphism? So R and Q are same as quotients. Then, like we concluded that Q is a an epimorphism? I mean, yeah, I mean, you concluded that it's co-kernel. So co-kernel of Q, which is co-kernel of J. Yeah, this is 0. And that's all we wanted to show. So a lot of diagram chasing here. Okay, if you are confused, then tell me where you are, at which step you lost me. Kernel of, yeah, I mean kernel of a mono is 0, yes. It's a mono if and only if it is kernel. Its kernel is 0. Yeah, in an abelian category you can show that. So therefore co-kernel of Q is 0, which means Q is an epi. Are you still confused? Okay, so this is existence and uniqueness of image factorization. Let me state some properties of abelian categories. As I already pointed out, please look at the definition. It is pre-additive. And we already established that if A is pre-additive, then so is A op. Then it is additive, which means it has 0 object, which is both terminal and initial. Then it has byproduct, which are both binary coproducts and binary products. Then it has kernels as well as co-kernels. Then every mono is normal and every epi is normal. So it is a self-dual definition. So the first property that we can write down is that A is abelian if and only if A op is. And therefore, thanks to our duality principle, which you may have forgotten, we covered it quite in the beginning of the course. You only need to prove results about kernels and products. The corresponding dual results will automatically follow. You don't have to do any extra work for them. Yes, so duality principle is applicable. Okay, from the result that we just proved, yeah, that subobjects there is a bijection between subobjects of an object A and the quotient objects of A. Subobjects are isomorphism classes of monomorphisms. Similarly, quotient objects are isomorphism classes of epimorphisms with that target. You forgot, okay, fine, but it's a monomorphism and equivalence class of monomorphisms under less equal intersection greater equal. We have done the pre-Posetel reflection. Yeah, so those are subobjects. So similarly, you do the same thing with epimorphisms with the same domain instead of codomain. What is this bijection? So given by, yeah, I mean I'm just going to write sub of A. Correct. So quotients of A. So this is co-kernel and this is kernel. Okay. So any abelian category is balanced. What is the meaning of balanced? Mono plus epi is iso. But every mono is normal and regular mono plus epi is always iso. So therefore, any abelian category is balanced. There is a fourth property which I am going to state now. Yeah, that given any pullback diagram, let me call it P, then A, B and C. This is F, G, K and H with F epi. Okay. So if F were mono, then what can you say about K? K is mono. Because monomorphisms are defined like they are compatible with pullbacks. Yeah, you remember we have done that. In any category, pullback of a mono is mono. But here I am going to say something different. Okay, so given any pullback diagram with F epic, this square is also a push out and K is epic. So pullback of an epimorphism is an epimorphism, which is not what you normally think about. Yeah? Epic and monic. That's how we write. Mono or API, that's also fine. Yes, similar thing. Okay, so let's prove this. When does this diagram commute? Yeah, the square commutes. I mean, okay, let's first consider something that might be familiar to some of you. So consider the sequence of morphisms. So this is P, then this is A direct sum B, and this is C. Here I am going to write HK, a matrix map, and here I am going to write F comma minus G. You understand this diagram? Yeah, H comma K, this matrix notation simply denotes that you are going from P to A via H and P to B via K. And then A direct sum B to C, F minus G map takes little a comma little b and it sends it to Fa minus Gb. We can do subtraction, so therefore we are allowed to do this. Okay, so the square commutes if and only if F comma minus G composed with HK is equal to 0, which is given to us. Yeah, we are given that the square commutes, so therefore we know F comma minus G composed with HK is equal to 0 because it's simply FH minus GK. FH is equal to GK, so FH minus GK is 0. Okay, then the square is the pullback, yes, is a pullback diagram. Yes, if and only if yes, HK is the kernel of F minus G, and similarly there is another statement, and the square is a push out if and only if F comma minus G is the co-kernel of HK. Okay, so all these properties are true. So basically, see, what we are doing is we are converting the data of a pullback or a commutative square into a sequence of morphisms. Yeah, we are trying to go towards chain complexes, exactness, homological algebra. But for that, like, this is just a baby step in that direction. So square is a push out if and only if this happens, is the co-kernel of this. Okay, But what is given? But f is epi. Okay, so therefore f comma, like it implies that f comma minus g is epic, since f can be written as f comma minus g composed with 1 comma 0. Yeah, and like a very basic elementary exercise, that the second factor of an epimorphism is always an epimorphism. So therefore it is an epimorphism. Okay, so then what do we get? So therefore f is ap plus the square commutes. Square is a pullback. Put both of those pieces together, this will imply that f minus g is isomorphic to the co-kernel of the kernel of f minus g. Yeah, which is isomorphic to co-kernel of h comma k. In the second step, I am using that it is a pullback. In the first step, I am using that it is epimorphism. So any epimorphism is isomorphic to its own co-image. So, but kernel of f minus g is h comma k. So therefore, we obtained the necessary and sufficient condition for this diagram to be a push out. Okay, good. So, therefore the square is a push out. One last thing remaining to check is we have to show that this is epimorphism. Yeah, so let me make some changes in this diagram itself. Let me add a bit of notes. So I want to show it's an epimorphism. So which means if I take its co-kernel, so let me call this Q, which is co-kernel of K. What do I need to show it to be? 0. Yeah. Now I should first complete it to a commutative diagram. Well, co-kernel K composed with K is always 0. So it's enough for me to take 0 map here so that the outer rectangle commutes. Now we have just shown that it is a push out. So by push out property, like this thing. So by push out property, I have existence of a map. Let me call it R. So what can I conclude from R? RF is equal to 0. Yeah, so RG is equal to Q and RF is equal to 0. But F is an epimorphism. So therefore R is equal to 0. So therefore this implies, these two things together imply that Q equal to 0. So Q equal to 0, which means K is indeed an epimorphism. Okay, let's stop here. Do you have any questions? Next time we are going to start looking at some spatial types of Abelian categories called Grothendieck Abelian categories, and we'll give a sketch proof of Freid-Michel embedding theorem, which states that any small Abelian category can be thought of as can be embedded in a fully faithful manner in a module category over some ring. Yeah, very beautiful proof. And that particular theorem actually allows you to view every small Abelian category as a concrete category, which means whatever diagrams we have been chasing, we can talk about elements inside P, elements inside A, elements inside B and C. Yeah, so the diagram chasing makes sense thanks to Freid-Michel embedding theorem. Let's stop.